in the name of science is this? Oh my, science!
What is up, everybody? This is Sean Murray for Oh My Science, and today we're going to be doing a deeper dive into the science behind scanning electron microscope images. Now, this is a follow-up to my previous videos. If you haven't seen that, I'll put a link in the show notes below. So just to rehash, a scanning electron microscope, or SEM for short, is used to produce high magnification images. It does this by heating up a filament under vacuum and creating a beam of electrons which are then directed onto the surface of your sample. Electrons that bounce back from the sample are then captured by a detector, which are then used to produce an image. What I want to discuss today is what exactly happens when this electron beam hits the surface of your sample. If your brain works like mine does, you're probably thinking that this interaction looks a bit like a ball bouncing on the ground, where the electron hits the surface and bounces back into the detector. But in actuality, it is probably better represented by a bullet being shot at a watermelon that explodes into a million pieces. This is because the particles in the electron beam are moving with such intense speed and energy that they are capable of breaking apart the individual atoms that make up matter and sending them scattering. So there are a multitude of particles that get scattered when an electron beam hits a sample, just like the pieces of the watermelon. But I'm going to talk about the two most commonly measured: secondary electrons and backscattered electrons, as well as a byproduct of their production, X-rays. To explain this, you first need to consider that every piece of matter, including the samples we put into the SEM, are composed of bajillions of individual atoms, with a nucleus that is being orbited by a cloud of free-floating electrons. Now, when we fire the electron beam at a sample's surface, these extremely tiny, high-energy particles penetrate the sample's surface and continue on until they interact with something. Depending on what that something is, will determine what particles get scattered. Now, in the case of a backscattered electron, what happens is an electron from the beam enters into an atom but comes too close to the nucleus. Since an electron has a negative charge and a nucleus has a positive charge, the natural attraction between the two can cause the electron to swing around the nucleus and get shot back out. Kind of like those gravitational assists around a planet or a black hole that every sci-fi movie loves to use to speed up their spaceships. Now, because backscattered electrons never actually hit anything and are instead just redirected by the positive attraction of the nucleus, these particles still maintain a very high energy. This means that backscattered electrons can escape a sample even if they form very deep within. So when you look at SEM images produced using backscattered electrons, you have more information from below the sample's surface. This means you lose some detail from the surface, such as texture and depth. If we look at a schematic of the excitation volume, the area that is affected by the electrons from the beam when it hits the sample, you can see that the depth of the area that forms backscattered electrons extends to a few microns below the sample's surface. If we compare the excitation volume of backscattered electrons to secondary electrons, the other primary particle used for producing SEM images, secondary electrons are only produced from the upper tens of nanometers below the sample's surface. This means they give much more information on what the surface of a sample looks like. This is because secondary electrons are formed with much less energy than backscattered electrons, so they can't escape the sample from very large depths. These low-energy secondary electrons are formed when the electron beam impacts an electron from an atom in the sample. Yeah, that's right. We actually managed to bullseye a particle that is 2.82 times 10 to the negative 15 meters across. That's a femtometer. I actually had to go look that up. And we managed to do it with a particle that is the exact same size. I mean, SEMs are basically just Jedis blowing up Death Stars. This is absurd. But the SEM is able to do it over and over again by shooting so many electrons at the sample. And when it happens, the electron that it hits gets deflected out of the electron cloud in your sample and then is captured by the SEM. Once the SEM produces its image from all of the secondary electrons that we just blew out of the sky, what is left behind are a bunch of giant gaping holes in the electron clouds of the atoms in the sample. If these holes are from the inner rings, that makes the atom very unstable. So it needs to fill that hole with another electron. What ends up happening is an electron from one of the outer shells will move in to take the place of the inner electron and maintain that stability. However, the energy difference between an electron in the outer shells compared to the inner shells is very different. So in order to make that transition, the outer shell electron needs to release some of its energy so that it fits better into the hole in the inner shell. It does this by producing an X-ray. Because the difference in energy between the shells of an atom are different for every element on the periodic table, the energy of the X-rays that are produced have a unique signature that can be used to characterize the elements they came from. We can therefore measure these X-rays to actually tell us what elements are in our samples. This method is called energy dispersive spectroscopy, or EDS. To show you what that looks like, I have taken an EDS measurement from two spots on the same backscatter image. One from the bright spot and one from the darker spot. Now, because this spot is significantly brighter, I would expect that it would have a higher concentration of high atomic number atoms in it than this darker spot, as those contribute to the brightness in the image. The EDS spectra is composed of a series of peaks which represent the energy of the X-rays when they are picked up by the detector. The height of these peaks are correlated with the abundance of each element in the chosen spot. So, if I am looking at the same peak between two different samples, a higher peak in one sample suggests a greater proportional abundance of an element within that spot. If you compare the EDS spectra from these two spots, we can see that my inference was correct, as the darker spot has a greater proportion of the lighter elements, magnesium and silica, while the brighter spot has more heavier elements, iron and nickel. Once you start measuring the EDS spectra on specific points in your sample, you can actually go a level deeper and start measuring elemental maps of the entire area. In this image, we have a backscatter map of a carbonate rock. You can see a series of bright spots and dark spots, suggesting a variety of minerals with light elements and heavy elements. Looking at an EDS map of this region, you begin to see the distribution of elements throughout the sample. With some of the newest technology, it is even possible to use the EDS spectra to go one step further and identify not just the elements, but the different minerals that contain those elements in your samples. So that's all I got for today. I hope you learned a little bit about how backscatter electrons and secondary electrons can be used to produce SEM images, and all the cool things that we can actually do once we start measuring them. I'm Sean Murray, your Oh My Science guy here at Macquarie University. And remember, if you have any questions, don't hesitate to ask. Take care.